Alright, so today I'm gonna be explaining this beautiful paper with the title Autoregressive Diffusion Model for Graph Generation. This ICML paper in 2023. Diffusion-based graph generative models have recently obtained promising results for graph generation. However, existing diffusion-based graph generative models are mostly one-shot generative models that apply Gaussian diffusion in the dequantized adjacency metric space. Such a strategy can suffer from difficulty in obtaining in model training, slow sampling speed, and incapability of incorporating constraints. So we propose an autoregressive diffusion model for graph generation. Unlike existing methods, we define a node-absorbing diffusion process that operates directly in the discrete graph space. For forward diffusion, we design a diffusion ordering network which learns a data-dependent node-absorbing ordering from graph topology. For reverse generation, we design a denoising network that uses the reverse node ordering to efficiently reconstruct the graph by predicting the node type of the new node and its edges with previously denoised nodes at the time. Based on the permutation invariance of graph, we show that the two networks can be jointly trained by optimizing a simple lower bound of data likelihood. So you need to know what is absorbing this discrete diffusion. An absorbing diffusion is a Markov destruction process defined in the discrete state space. At transition time step t, each element x sub t, each element is in dimension I, is independently decayed into an absorbing state with probability alpha t. The absorbing state can be mask token for task or gray pixel for images, or again mask for node, mask for node type, mask for edge type. That is the absorbing state. That could be one of the absorbing state that you can define in your model. The diffusion process will converge to a stationary distribution that has all the mass on the absorbing state. The reverse of the absorbing diffusion is learned with categorical distribution to generate the original data. Typically, the decaying probability need to be small and the diffusion steps need to be large to attain good performance. You also need to know what is autoregressive diffusion. An autoregressive diffusion is a stochastic absorbing process where exactly one dimension decays to the absorbing state at a time. The diffusions is repeated until all dimensions are masked or absorbed, like masked. So now they want to use it for graphs. So what is absorbing node state? When a node enters the absorbing state, it will be masked and it will be connected to all other nodes in G by masked edges. You see the autoregressive diffusion process that the nodes are autoregressively decayed into until they reach the fully absorbing states. All nodes are absorbing states. So we have an ordering generated by diffusion ordering. So we say, for example, we draw 2. So we say node 2 should be masked. So it's one at a time. That's why these autoregressive methods are very slow, because it's just one at a time. Note that we do not need to consider the graph automorphism, since the diffusion process assigns a unique ID to each node to obtain the decay ordering. So now you see the generated procedure at step t with the denoising network. the reverse one is like you want to learn this. You have some parameters, theta for this graph attention network, which is your denoiser. This is your denoiser. You want to understand what is the GT, give it condition and GT plus 1. So one step less. So the next denoising step is here. So you have node prediction and the edge prediction. So in autoregressive graph diffusion, the node decay ordering sigma is sampled from a diffusion ordering network. Then exactly one node decays in the absorbing state at the time. This paper has many citations because after this paper, many papers came and generalized this idea. For example, this paper is just autoregressive. Then some people use any order autoregressive. Some people said some parallel doing you do parallel. In parallel you do masking. You don't need to do one at a time. So there is another generalization using paired, that Carnegie Mellon model from Carnegie Mellon University, paired model, which is permutation invariant as well. And they just do sequentially, and at each time you add a couple of nodes. The next time you add another couple of, but in each time step there is a whole diffusion process. There are many ways to look at this masking, to look at this let's say absorbing process in general. The denoising network, if you use graph attention network, so you need to learn the coefficients. So the training is very simple. You just use variational lower bound. This is the discrete version of the variational lower bound because it's discrete time. And so ordering represents the node type of V sigma and its edges at this O. When we see O, that you see in the loss of the training. This is the node types. So with all previously denoised nodes. But the architecture of this paper RDM in 2022 predicts all mask dimensions simultaneously. As I said, some papers use parallel thing. So which enables training the on univariate conditionals in parallel. So graph arm, due to the node permutation invariant property, this parallel can be simplified as training with just the soft label. So the weights of that are just Q phi, Q phi. In practice, the probability mass might be concentrated around a small set of remaining nodes. So it is generally sufficient to consider only those node labels with associated high probabilities. So each training iteration, we explore the diffusion ordering network by creating M diffusion trajectories for each training. But for learning, they used reinforce. The diffusion ordering networks can be updated with the common reinforcement learning. But these reinforced algorithm has high variance. So when you just use this, it has some problem of variance. But this is a very good paper. And it has many citations because the idea of absorbing sets is very, very intuitive from distribution point of view. So they did experiments on Cora dataset, ego small enzyme breast dataset, and they compare even digress. So it's even sometimes better than digress, this graph arm model. So in computer vision, we have images, so we have Frecce inception distance. But for graph, this becomes Frecce chemical net distance. So this FCD, Frecce chemical distance, this should be low, because all distances should be low. The lower, the better. That's why we use this mark. So for QM9, they compared digress with graph arm. And you see sometimes digress has a better validity. For example, validity of digress is 99, but graph arm has less validity. Do you know why? Because it's an autoregressive, and at each time, if you do any mistake, then you cannot turn mask into something else. So there is no update and replace. So some papers, I've seen some papers that they have resolved this issue. So they created in their transition some update and replace. So they call it alpha, probability of keeping it, beta, probability of masking, and then another interesting thing, probability of replacing, gamma. Of course, alpha plus beta plus gamma should be 1 in order to be well posed. So this is the training procedure of graph arm. Here they compute reward because they're using that reinforce algorithm to learn the ordering. And then, so they start by some ordering network and denoising network. So for denoising, they update the parameters of denoiser using this. And then we sample from validation. For validation, we obtain trajectories. We sample T and then compute the reward, and we update the parameters of the ordering network. So this is their network architecture. This is their denoising network. So they have 5 layers of message passing. It means it takes 5 layers to reach from one node to another node, which is 5 hop away. Similarly, for edges, they have defined this. And this is the visualization of generation ordering. This is for QM9, generated samples from QM9. This is for generative samples for Zinc 250K